Okay, welcome to the terminal, everyone. If you're currently preparing for the Cambridge 9709 Probability and Statistics 1 exam, you already know the frustration. You totally understand basic probability, you've memorized the addition rules, you get conditional probability, and yet you're still leaking easy marks on the actual paper. Why? Well, because simply mastering the math isn't enough anymore. Today, we're running this explainer like a Silicon Valley hackathon. I'm going to be your lead dev, and we are going to treat your next high-tariff exam paper as our target mainframe. We're going to optimize your performance by treating these complex multi-part problems as pure code. We'll show you exactly how to systematically debug them, transforming your raw mathematical knowledge into a precise algorithmic sequence that clears the examiner's firewall every single time.
We've mapped out a very precise blueprint for today's system update. We're going from the core principles straight through the method mark strategy, executing the standardized sequence, and finally debugging errors.
So, to kick things off, let's look at Section 1, the theoretical architecture of the exam, or as we like to call it, the core system requirements.
Now, to understand these requirements, I want you to picture two junior developers on our team. Let's call them Dev Alex and Dev Sam. Now, Alex is incredible at raw data inputs. He can memorize formulas like nobody's business, but he constantly causes memory leaks in his code because his analysis is super shallow. The Cambridge Assessment Framework explicitly targets this. It prioritizes analytical depth over superficial breadth. They don't just want to see that Dev Alex memorize the formula for conditional probability. They need him to prove exactly why the probability of A given B restricts the sample space to only event B. It's not about blindly plugging numbers into a fraction, it's about proving the underlying architecture of your logic. The system is testing your processing power, not just your hard drive storage. And this is exactly where the principal examiner reports step in. They explicitly highlight that candidates who reference cross-topic connections achieve significantly higher marks. Imagine you're working on a probability algorithm involving drawing colored marbles from a bag without replacement. The examiners want to see you flawlessly integrate permutations and combinations right into that probability framework. Treating these topics as isolated silos, like using simple counting when you absolutely need factorials or binomial coefficients, is a fatal system crash. It basically signals to the examiner that your mathematical subroutines aren't communicating with each other. Which brings us to a massive logic hurdle. Why exactly do students find evaluating evidence and drawing conclusions so difficult? Well, let's talk about our other coder, Dev Sam. Sam is great at setting up logical loops, but when he looks at a messy, multi-layered tree diagram, he panics. He drops his syntax precision and relies entirely on raw intuition to guess the final output. You just can't do that. You can't skip to the end of the code and expect it to compile perfectly. We have to pivot away from this guessing game and start mapping out our response as a structured command matrix. Let's move over to Section 2, the method mark strategy, where we actually start earning points just for running the process correctly. Okay, so here is the absolute game changer. The examiners heavily reward your systematic processing. Your clear working is literally just as vital as your final answer. If you just jot down the final probability of a mutually exclusive event without actually writing out the addition rule first, stating that the probability of A union B equals the probability of A plus the probability of B, you are leaving guaranteed method marks on the table. It's like writing a brilliant script but failing the syntax rules. The compiler will reject it. Even if you punch the wrong digit into your calculator at the very end, displaying the correct mathematical syntax acts as an automatic failsafe. The process is the product here, guys. To make sure we capture every single one of those method marks, let's boot up the execution protocol. This is the standardized sequence you need. You need to treat this sequence as your ultimate pseudocode. Let's run a quick test scenario, finding the probability of rolling a 6 on a biased die over multiple trials. Step 1, identify. Extract the key variables from the text prompt. What is the probability of success, and what's the exact number of trials? Step 2, apply. Select your logical framework. Are we deploying the binomial distribution model because we have fixed trials and independent events? Step 3, execute. Run the analysis with crystal clear notation. Write out that binomial formula line by line. Step 4, verify. Does your resulting decimal actually make mathematical sense? And finally, Step 5, present. Package the output in the appropriate format, which for Cambridge usually means rounding exactly to 3 significant figures. Follow this matrix and your code compiles flawlessly. This is the core deconstruct, solve, evaluate loop. Now, hold up. Before we push this final patch to secure maximum marks on the live server, we need to optimize your system feed. Take a second right now to subscribe to Ace the Exams at the handle @AceTheExams and turn on all notifications so you never miss our weekly system updates. Okay, patch compiled, let's resume.
Imagine you hit a massive logic error mid-argument. To debug it, you deploy the Peel syntax structure: point, evidence, evaluate, link. You deconstruct the props to extract the variables, systematically execute the solve phase, and then, crucially, evaluate for reasonableness. If your calculated probability outputs as 1.5 or a negative integer, your script has a catastrophic bug. Probabilities literally only exist between 0 and 1. Catching that allows you to loop back and debug the error before deploying the final answer.
To hard code this sequence into your brain before exam day, the source material highly recommends building your own custom mnemonic. Think of it as a custom keyboard shortcut. For example, to remember identify, apply, execute, verify, present, you might use I always execute valid programs. Having that mental trigger ready saves you massive amounts of processing power when the exam clock is ticking down, freeing up your RAM to focus entirely on the math.
Let's transition into Section 4. Welcome to the interactive beta testing arena, where we are going to look at debugging the most common errors straight from the examiner logs.
Imagine a 60-second visual countdown clock ticking on your screen right now for a data extraction run. Examiners consistently flag that candidates confuse key terminology. It's a massive vulnerability. If you're running an analysis on independent events, you can't just casually drop the word into your text. Your code must clearly show the mathematical condition that the probability of A intersecting with B exactly equals the probability of A multiplied by the probability of B, or showing that the probability of A given B equals the probability of A. Defining these terms with hard mathematical syntax before you calculate is absolutely mandatory to bypass the examiner's firewall.
Let's do a quick code review. Here are the top 3 bugs that will instantly cross your score. Bug number 1, confusing cause and effect. In conditional probability, mixing up the probability of A given B with the probability of B given A is a fatal logic error. They are mathematically distinct parameters. Bug number 2, format failure. If you round your decimals too early in intermediate steps or drop your standard notation, you immediately lose method marks. Bug number 3, lack of context. If you output a generic statistical block that ignores whether the data is about choosing committee members or drawing playing cards, the system flags your analytical depth as too shallow.
By contrasting these raw text blocks, we see the stark difference between basic input and optimized top-tier evaluation. A typical student operates like an outdated calculator, blindly crunching variables, completely ignoring the real-world context of the probability model, and just praying the final digit matches the mark scheme. But a top-scoring candidate, they run a high-level evaluative routine. They interpret the relationships, they sanity check their outputs against reality, and they compile a concluding statement that directly addresses the specific target prompt. Demonstrating this exact level of evaluative thinking is the master key to the highest mark bands. The examiner's logs are crystal clear on this. The best developers exhibit a conceptual understanding that transfers seamlessly to completely unfamiliar, even totally weird contexts. They don't just solve the equation, they actively question the assumptions, they consider alternative parameters, and most importantly, they heavily justify every single decision with hard statistical evidence. They treat the math as a dynamic tool to solve a real-world problem, not just a static number to underline twice at the bottom of the page.
So, as we initiate the final code deployment and wrap up this explainer, I'll leave you with this. When you log into that exam hall, are you going to rely on raw, unstructured intuition, or are you going to execute this proven step-by-step algorithm? By understanding the exact system requirements, sticking to the standardized protocol, and debugging those common errors, you are building the ultimate cheat sheet architecture in your mind. Statistics is the underlying source code for understanding risk in the real world. Learn to read it, and you can predict almost anything. That's all for today's hackathon. Do not forget to subscribe to Ace the Exams at @AceTheExams. Absolutely smash that notification bell and leave a comment below with your exact subject and tier level so we can target our next patch specifically for you. Keep optimizing, and I'll see you in the next update.